Today, we're looking behind the scenes at something, well, hidden, but absolutely essential for almost every structure around us. Think bridges, buildings, pretty much everything. We're talking about welding consumables. Now, welding consumables, that basically means anything that gets used up when you make a weld. It's quite a big list, actually, gases, wires, fluxes. But for this deep dive, we're going to really zoom in. We're focusing on a very specific and surprisingly complex area, the electrodes used in manual metal arc welding. You might know it as MMA welding.
That's right. Yeah. Today is all about those MMA welding electrodes. And you really shouldn't think of them as just, a metal stick. It's much more like choosing a very precise, specialized tool for, say, a complex surgery. Getting the right electrode and handling it correctly, that's fundamental. It really determines the success, the strength, the whole integrity of the weld.
Okay, so here's our ambition for you listening. By the time we wrap this up, you'll have a much deeper appreciation for what actually makes an MMA electrode work. We'll dig into why there are so many different kinds, what jobs each one is best suited for, and crucially, why taking care of them is so incredibly important. Get ready, because there's some surprising science packed into these seemingly simple rods. Right, let's get into it then. An MMA electrode, it looks pretty straightforward, doesn't it? Just a coated metal rod. But I guess that simple look hides quite a bit.
Oh, absolutely. That's the biggest misconception, that it is simple. It's actually quite a sophisticated bit of engineering. You've got the core wire, usually about 350 to 450 millimeters long, maybe 2.5 to 6 mils in diameter. But the real action, the complexity, it's all in that flux coating that's extruded around the core wire. And what's really interesting, perhaps counterintuitive, is that the core wire itself is often just a basic low-quality rimming steel.
Rimming steel. That does sound a bit basic for something that needs to be strong.
It does, doesn't it? But here's the clever part. The weld itself is essentially a casting process. All the purification, the refinement, adding the good stuff back in, that all happens because of the flux coating. It's like this tiny, self-contained chemical factory that just springs into action the second you strike that arc. It's really amazing how much is going on in that coating.
Okay, so what kind of jobs is this chemical factory doing?
Well, it does a whole bunch of really vital things during the weld. First off, it helps you start the arc easily and keeps it burning smoothly, stable. Then, as it burns, it decomposes and creates a shielding gas. Think of it like a protective bubble around the molten metal.
Ah, to keep the air out.
Exactly. Without that shield, the oxygen and nitrogen in the air would react with the hot metal, and you'd end up with a brittle, weak weld. Nobody wants that. The flux also acts like a cleaner, refining the weld metal as it solidifies. It pulls impurities out, trapping them in that layer of slag that forms on top.
Right, the slag. I've seen that glassy stuff on welds.
Mm-hmm. And that slag does double duty. It forms a protective blanket over the cooling weld, helps control the cooling rate, and gives further protection from the air. But wait, there's more. This coating isn't just passive. It can actively add alloying elements into the weld pool.
Really? Like what?
Well, you might have silicon in there to deoxidize the weld, get rid of oxygen, or manganese, sometimes up to about 1.6%, which really bumps up the strength and toughness of the final weld metal. And maybe most critically for certain applications, it controls the hydrogen content.
Hydrogen. Why is that so important?
Because too much hydrogen getting dissolved in the weld metal can lead to a really nasty defect called hydrogen-induced cold cracking. It can happen hours, even days after welding, and it seriously compromises the joint.
Okay, that sounds bad.
It is. So controlling hydrogen is key. And finally, the flux even helps physically shape the arc. It forms a little cup or cone at the electrode tip, which helps direct the arc energy precisely where the welder needs it.
Wow. Okay, that's a lot more going on than just metal stick.
Told you. It's proper engineering.
All right, so now that we know what's packed inside, let's talk about how these different recipes lead to different types of electrodes for different jobs. This is where we meet the main players, right? MMA electrodes are basically grouped by what's mainly in that flux coating, and each group has its own distinct personality and uses. We'll look at the three big ones: cellulosic, rutile, and basic.
Okay, first up, the cellulosic electrode. You could call this one the deep penetrator. Its main ingredient is cellulose, basically plant fiber, an organic material. What makes it stand out is the gas shield it produces. It's very, very high in hydrogen. We're talking 80, maybe 90 milliliters per 100 grams of weld metal. That's huge.
And that hydrogen gives it the penetration.
Exactly. It creates a really fierce digging arc. This means you get deep penetration and excellent fusion between the weld and the base metal. That lets you weld quite fast without worrying about lack of fusion, which is a potential weak spot. Because of this, cellulosic electrodes are fantastic for welding in all positions, flat, vertical, overhead. They're particularly famous for pipe route runs. There's even a technique called stovepipe welding, often used on pipelines, that relies heavily on these.
Sound powerful, but high hydrogen. Did you say that was a risk?
Yes. That's the major drawback. That high hydrogen brings a significant risk of hydrogen-induced cold cracking, especially in thicker materials or higher-strength steels. So you generally wouldn't use cellulosic on, say, steels stronger than API grade X70 or on sections thicker than about 35 millimeters or so. They also don't offer great toughness at low temperatures, maybe okay down to about minus 20 Celsius, but not much colder. And frankly, they produce a lot of fumes and spatter, and the finished weld can look a bit rough.
Okay. And a key point on handling.
Absolutely critical. Never bake or dry cellulosic electrodes. It ruins the coating. You use them straight from the sealed container. No preheating needed.
Right. So cellulosic, fast, deep penetration, great for pipes, but handle with care regarding hydrogen thickness and temperature. Not for everything.
Precisely. It's a specialist tool. You wouldn't use it where that hydrogen risk is unacceptable, like on really critical high-strength joints. For those, you'd definitely reach for something else.
Which brings us neatly to the next type.
Indeed. Let's talk about the Rutile electrode. This one is genuinely the general-purpose all-rounder. The key ingredient here is titanium dioxide, TiO2. It's a great slag former and helps stabilize the arc. These are probably the most user-friendly electrodes out there. They're known for being really easy to strike an arc with. They produce much less spatter than cellulosics, and the arc itself is very smooth and stable. Works well on both AC and DC currents, too.
And the finish.
Usually very good. The slag typically peels off really easily, leaving a nice, smooth weld profile. Plus, they give decent weld metal strength. They're just easy to work with.
So where do you see these used most often?
Oh, all over the place in general fabrication. Think low-pressure pipework, support brackets, general steelwork repairs. They're incredibly versatile for everyday tasks. Now, regarding hydrogen, you can dry them gently to lower the content a bit, maybe down to 25 or 30 milliliters per 100 gram pressure. But like cellulosics, you absolutely cannot bake them at high temperatures. It destroys the coating.
So it's still some hydrogen, but less than cellulosic.
Yes, significantly less. But their main limitation is that you can't get them down to very low hydrogen levels. That means they're generally not suitable for high-strength steels or really thick joints where that hydrogen cracking risk becomes a major concern again. And similar to cellulosics, they don't offer particularly good toughness at very low temperatures. Great all-rounders, but not for the most demanding high-integrity jobs.
And didn't you mention a sort of souped-up version?
Yes, the high-recovery rutile. Good point. These have iron powder added into the flux coating, sometimes a lot of it. This dramatically increases the deposition rate, how much weld metal you lay down. You can get efficiencies up to like 180% of the core wire weight.
Wow, so much faster welding.
Exactly, higher productivity. And because you're depositing so much metal, you tend to get these larger, smoother weld beads. Sometimes they almost look like welds made by a machine process, like submerged arc welding.
What's the catch?
The catch is that big fluid weld pool. It means you're pretty much limited to welding flat downhand, the PA position, or horizontally, the PB position. Trying to weld vertical or overhead with that much molten metal, well, it's just not practical. Gravity wins.
Makes sense. Okay, so we've had the deep penetrator and the all-rounder. What's the third type?
The third main group is the basic electrode. Think of this one as the high-performance expert, or maybe the low-hydrogen hero. Their flux coating is based on calcium compounds, things like calcium fluoride and calcium carbonate. Chemically basic, hence the name. These tend to produce a weld bead that's a bit more convex, sort of bulges outward slightly. And the slag, sometimes it can be a little trickier to remove compared to a rutile slag.
But their performance must be special.
Oh, absolutely. Basic electrodes are indispensable for the really critical stuff. We're talking high-pressure systems, very thick steel sections, high-strength steels, anywhere that weld quality and structural integrity are absolutely non-negotiable. They consistently deliver excellent toughness, even at low temperatures and high yield strength. But their defining characteristic, their superpower, is hydrogen control.
The low hydrogen aspect again.
Exactly. Basic electrodes are specifically designed to achieve the lowest possible hydrogen levels in the weld metal. Properly handled, we're talking less than 5 milliliters per 100 grams of weld metal. Some even go lower, like H4 classification.
That's incredibly low compared to the others.
It is, and that's precisely why they are the go-to choice for critical applications. Minimizing that hydrogen virtually eliminates the risk of hydrogen-induced cracking.
So what are the downsides? There must be some.
There are. They generally cost more than rutile electrodes. They also demand a higher level of welder skill to use properly. The arc characteristics are a bit different, less soft than a rutile. And crucially, they require extremely meticulous control over storage and pre-use procedures to maintain that low hydrogen potential. We'll probably talk more about that later.
Okay, so the basic electrode, the top performer for strength, toughness, and safety against cracking, especially in demanding situations. But it requires more investment, more skill, and very careful handling. The precision tool.
That's a perfect summary. It's the choice when failure is simply not an option.
Right. This leads us nicely into something else you see on the packaging. All those codes like E6013 or maybe something longer like E43219RR. They look like, I don't know, secret messages.
They might seem like it, but they're far from secret. In fact, they're a critical communication system. It's not just jargon, it's the universal language that welders, engineers, inspectors, everyone uses worldwide to ensure they've got the right product for the job.
A universal language for welding electrodes.
Pretty much. These classification systems, the main ones are EM ISO 2560, which is common internationally, and the AWS A5.1 or A5.5 specs from the American Welding Society. They're like a detailed spec sheet, or as you said earlier, like a nutritional label for the electrode. They tell you vital information, the minimum strength the weld should have, the chemical composition, what positions you can weld in, the type of current to use, and yes, very importantly, the potential hydrogen level and any special care needed.
So they pack a lot of info into that short code.
They really do. Let's break down a couple of simple examples. Take an AWS code like E7018, the 70 tells you the minimum tensile strength is 70,000 psi. If you saw an EN ISO code like E46, the 46 means 460 newtons per square millimeter minimum yield strength. So first part, usually strength.
Okay, strength.
Welding position is often in there. In that AWS E7018 example, the 1 indicates it's suitable for all positions flat, horizontal, vertical, overhead. A 2 would typically mean only flat and horizontal.
Right.
And the last digit, or sometimes the last 2, tells you about the coating type and usability. That 8 pun in E7018. It signifies a basic, low-hydrogen coating with iron powder, usually run on DC positive. And E6013, that 3 point, tells you it's a rutile coating, usable with AC or DC.
And the hydrogen level.
That's often indicated too, especially in the EN ISO system. You might see something like H5 tacked onto the end of the code. That specifically means the diffusible hydrogen content is guaranteed to be less than 5 milliliters per 100 grams of deposited weld metal if handled correctly.
So H5 is very low hydrogen.
Very low, yes. That's typical for a basic electrode classification. Rutile might be H10 or H15 if tested. Cellulosic much higher, often not even classified for hydrogen in the same way because it's inherently high.
Okay, I see. So this code isn't just random numbers and letters. It allows an engineer to specify exactly the electrode needed for a particular steel, a particular joint design, a particular service condition, ensuring safety and quality.
Precisely. It removes ambiguity. Everyone is working from the same playbook, ensuring the final structure performs as designed. It's fundamental to quality control in welding.
Which brings us to, well, handling them correctly. We talked about the science inside the electrode, the clever flux. But how they're treated before they even get near the arc seems just as vital. This is the golden rule you mentioned earlier, isn't it? Care and storage. It's not just about being tidy.
Absolutely not just about tidiness.
Yeah.
Proper storage and handling are non-negotiable for all welding consumables, but they are especially critical for MMA electrodes because of that flux coating. When electrodes arrive on site, or even in a workshop, there should be checks. Are they the right size? The right type, matching the specification? Are they physically damaged? Any cracks in the coating, chips, rust on the core wire? And crucially, how have they been stored? Because moisture is the enemy here.
Moisture, right, because it affects the flux.
Dramatically. Most flux coatings are hygroscopic to some degree, meaning they'll absorb moisture from the atmosphere. If they get damp, the coating starts to degrade. And all those carefully designed functions we talked about, the shielding, the cleaning, the alloying, can be compromised.
So keep them dry.
Bone dry. Ideally, electrodes should be stored in warm, dry conditions. Think controlled storerooms, maybe with dehumidifiers, aiming for close to 0% humidity if possible, especially for the sensitive types. And when we talk about basic electrodes, the low hydrogen ones, the procedures become extremely strict, highly regulated on critical projects.
Because that low hydrogen property is so vital.
It's their whole reason for being. If a basic electrode picks up moisture, it loses its low hydrogen characteristic, completely defeating the purpose of using it and reintroducing the risk of cracking. So, before use, basic electrodes must be baked. This isn't just gentle drying, it's a high-temperature bake in a calibrated oven, typically around 300 to 350 degrees Celsius. That's really hot for usually 1 to 2 hours.
Wow, 350 C. What does that do?
It drives out any absorbed moisture, restoring the electrode to its minimum hydrogen potential. It basically resets it to its as-manufactured low hydrogen state. But the care doesn't stop there. After baking, they're not just put on a shelf. They're transferred to holding ovens, kept at around 150 degrees C to prevent them reabsorbing moisture.
And then the welder takes them from there.
Usually, they're issued from the holding oven into heated quivers, portable containers the welder carries, which are kept warm, maybe around 70 degrees C or so. This keeps them dry right up until the moment of use.
That is incredibly meticulous. Baking, holding ovens, heated quivers, just for an electrode.
It sounds like a lot, but think about the cost comparison. A single electrode might cost, what, pennies? Maybe a little more for a specialized basic one? But the cost of repairing a crack caused by using a damp electrode on a critical structure, that could run into thousands, tens of thousands, even millions depending on the structure and the extent of the repair needed. Not to mention the safety implications.
Yeah, we put it like that.
Exactly. It's why you'll often see basic electrodes discarded at the end of a shift if they've been out in a quiver for too long, even if technically they could be rebaked maybe once or twice according to manufacturer's instructions. On many critical jobs, the risk is just deemed too high. It's cheaper and safer to just use fresh, properly conditioned ones.
That unwavering commitment to procedure really highlights the precision involved, doesn't it? It's not just striking an arc. It's controlling a whole process, right down to how you handle the consumables.
It absolutely is. It underpins the reliability of welded structures we all depend on.
Well, we've covered a lot of ground. We've gone from the basic core wire out to that complex flux coating. We've met the different personalities, the cellulosic penetrator, the Rutile all-rounder, the high-performance basic electrode. We've deciphered those classification codes and really hammered home why careful handling and storage, especially for low hydrogen types, is so utterly critical. Hopefully you listening now have a much deeper appreciation for these small but incredibly vital components.
Yeah, it is fascinating, isn't it, how much science and engineering goes into something that from a distance just looks like a metal stick. But the impact of choosing the right one and treating it correctly is just immense for the safety and longevity of everything from pipelines to power plants to bridges.
Absolutely. So the next time you see a construction site or hear about welding being done, maybe you'll picture that hidden world of these specialized consumables, each one selected, baked, stored, and used with real precision. And maybe that prompts a thought for you to consider. In your own work or your own field, what are those seemingly simple, maybe even consumable elements or foundational pieces that are actually doing incredibly complex and vital jobs? The things whose proper care and attention might be easily overlooked, but are actually fundamental to getting the right result. Something I'm all over. Thanks for diving deep with us today on MMA welding electrodes. We hope you feel a little more informed and maybe even a bit impressed by the humble welding rod.